The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. Okay, so today we're going to start Chapter 8, starting with section 8.2, part 1. We're going to spend today as well as Monday on section 8.2. And we're going to deal with something called a function. Okay, so let's talk about that. Let me read to you a description from the textbook. It says a function is a set of ordered pairs in which to each first component there corresponds exactly one second component. The set of first components is called the domain of the function, and the set of the second components is called the range of the function. I'm going to come back to that in a minute or two, but I want to look at a situation that I think we can all relate to. Let's talk about people and their birthdays. Let's say we have a group of people. Okay. We've got Jose and Mary and George and Susan. Okay. And we've got their birthdays. Okay. And let's say that Jose's birthday is April 2nd. Mary's birthday is May 5th. George's birthday is also May 5th, and Susan's birthday is March 9th. Okay, so here's what we can observe. Each person has exactly one birthday, discounting religious examples, of course. Anyway, sorry. Discounting religious experiences, that's what I wanted to say. Okay, so Jose's birthday, one date. Mary's birthday, one date. George's birthday, one date. Susan's birthday, one date. Now, Mary and George have the same birthday, but each of them only has one birthday, okay? Now, this relationship is just like a function. Let me read it again. A function is a set of ordered pairs in which to each first component, there corresponds exactly one second component. So the people are going to be the first component and the birthdays are going to be the second component. So for each first component, there's exactly one second component. Each person has exactly one birthday, okay? This would be the domain and this would be the range. Okay. Let's look at some examples, some further examples, some more examples. Here we have a set of ordered pairs. We have 7, -1, and -1, -11, and -5, 3, and 8, -6. So we have a set of 4 ordered pairs. It says find the domain and range of each relation. Okay, so the domain would be the x values, and I'm going to list them from smallest to largest. So -5, -1, 7 and 8. And the range would be all the y values. So that would be, let's see, -11, -6, -1, and 3. Okay. The hardest part of this is making these little bracket things. All right, so the domain is all the inputs, all the x values, the range is all the outputs or all the y values. Let's take a look at another example. Let's see here. Here we have the numbers 10, 20, and 30. And over here, the numbers 20, 40, and 60. And 10 goes to 20, 20 goes to 40, 30 goes to 60. Is this a function? Yes or no? Yes, it is. For each input, For each domain value, there's exactly one range value. So yes, this is a function. Now let's take a look at another example. -4, -2. In all these examples, the inputs on the left, the outputs on the right. And then we've got 6, 8, 10, and 12. -4 goes to 6, 2 goes to 8, 0 goes to 10, and 0 goes to 12. Is this a function? No, it's not. Give examples to show that it's not. Well, 0 goes to 10, but 0 also goes to 12. One input has more than one output. That's like one person with 2 birthdays. So this is not a function. Okay, let's take a look at some other examples. How about this one? -2, 4, -3, 8, -3, 12, and -4, 16. Is this a function? No, because -3 goes to 8 and -3 goes to 12. So because of those 2 points or ordered pairs, it's not a function. Okay. Another example. Let's see here. Let's look at table of values. We've got 1, 2, 3, 4, and 5, 7, 15, 23, 16, and 8. Is this a function? Yes, each input goes to exactly one output. How about this one? We've got 30 and 2, 4, 6, 8, and 10. Is this a function? No, it's not. Give 2 examples. Well, 32, 34. We've got one input going to a bunch of different outputs, so not a function. How about this one? Is this a function? Yes, it is. 5 different inputs going to the same output. 5 different people could have the same birthday. So yes, that's a function. All right, now, functions have special notation. The most commonly used symbol in function notation looks like that. It looks like an italicized F and then an X in parentheses. Now, this is just another name for Y, or for the output, okay? So it looks like, well, if you've got something and then parentheses, doesn't that look like multiplication? So F parentheses X, doesn't that look like F times X? But it's not. It's just a single symbol for Y. Also, the long way of saying this is F is a function of X. The shortcut way is to say F of X. Well, in many applications, the word of can mean multiplication. Like if you're dealing with 12 is what percent of 50? The word of implies multiplication. So F of X sounds like multiplication. So it looks like multiplication. It sounds like multiplication, but it's neither one. It's just, well, it's just the symbol F of X, and it's another name for Y. For instance, let's say I have the equation Y equals 2x plus 3. The function notation for that would be F of X equals 2x plus 3. Okay? Now, let's find some ordered pairs for this equation. Let's say we use -1, 0, 1, and 2 for x. If x is -1, y would equal 2 times -1 plus 3, which is -2 plus 3, which is 1. If x is 0, y equals 2 times 0 plus 3, which is 3. If x is 1, y equals 2 times 1 plus 3, which is 5. And if x is 2, y equals 2 times 2 plus 3, which is 7. So we've got these ordered pairs in a table form that are solutions to that equation. Now, let's take the related function, f of x equals 2x plus 3. To find the same pairs of numbers, I would say f of -1 equals, f of 0 equals, f of 1 equals, and f of 2 equals. So the input, or the x value, goes inside the parentheses. How do I find the resulting output? The same way I did with the equations. So f of -1 would be 2 times -1 plus 3, which is 1. F of 0 would be 2 times 0 plus 3, which is 3. F of 1 would be 2 times 1 plus 3, which is 5. And f of 2 would be 2 times 2 plus 3, which is 7. So this corresponds to that, which also corresponds to these ordered pairs. So here it is in a table, here it is as ordered pairs, here it is using function notation. Okay. Now, let's do some more examples dealing with that. Let's say we have the function f of x equals 3x minus 5. And we want to find f of 3 and f of -1. To find f of 3, we're going to put 3 in the place of x. So we'll get 3 times 3 minus 5, which is 9 minus 5, which is 4. So f of 3 equals 4. Again, that corresponds to the ordered pair 3, 4. If we were to graph this, it would look just like the graph of y equals 3x minus 5. The point 3, 4 would be a point on the graph. Okay. F of -1 is 3 times -1 minus 5, which is -3 minus 5, or -8. So f of -1 equals -8, which corresponds to the ordered pair -1, -8. All right. Let's see here. Let's take a look at g of x equals 5x squared plus 2x plus 2. Wait a minute, what do I mean g of x? Well, just like variables x and y, you can have other variables. Function notation, everything doesn't have to be f of x. You can have g of x or h of x or a of x. In fact, if this was a business algebra class, we might talk about a cost function, c of x, a revenue function, r of x, a profit function, p of x. So often that letter will stand for something specific. Here, g of x, it doesn't have any special meaning, but it could have. So if g of x equals 5x squared plus 2x plus 2, let's find g of 2. So that would be 5 times 2 squared plus 2 times 2 plus 2, which is 5 times 4 plus 4 plus 2, which is 20, plus 4 plus 2, which is 26. So g of 2 equals 26. All right. Let's take a look at another example. H of x equals x squared plus x minus 2 divided by x squared minus 5x. And let's find h of -2 and then h of 5. So h of -2, we're going to put -2 in the place of x everywhere it appears on the right side of the equal sign. So we're going to have -2 the quantity squared plus -2 minus 2 over -2, the quantity squared, minus 5 times -2, which is, let's see, -2, the quantity squared would be 4, and then -2, that would be 0 on top. -2 squared is 4, minus 5 times -2 would be plus 10, which is 14. But 0 divided by 14 is 0. So h of -2 equals 0, which is a point on a graph. Let's take a look at h of 5. That's going to be 5 squared plus 5 minus 2 over 5 squared, minus 5 times 5. So in the numerator, we've got 25 plus 5 minus 2. In the denominator, we've got 25 minus 25. So we get what? 28 over 0, which is undefined. Now, we can't graph undefined. Undefined doesn't exist. So what that tells us is that when we put 5 into this function, we don't get a real output. That means that 5 is not in the domain of the function because it's not an acceptable input, because when you put it into the function and turn the crank, you get undefined. You get something that's not real. And for something to be an acceptable input, it has to produce a real output. Okay. Now, let's say I've got g of x equals 3x. Okay. G of 2 would be 3 times 2 equals 6. G of -4 would be 3 times -4 equals -12. How about G of w? Well, that would just be 3w, because you'd take the w, the thing that's inside the parentheses, and replace x on the left or the right side of the equation. Okay. What about G of w plus 1? Well, you'd have 3 times the quantity w plus 1, which would be 3w plus 3 after we distribute. Okay. Let's see here. Let's say we've got g of x equals 2x. Getting ahead of myself here. 2x minus 7. G of w would be 2w minus 7. G of w plus 1 would be 2 times w plus 1 minus 7, or 2w plus 2 minus 7, or 2w minus 5. What about G of star? That would be 2 star minus 7. G of dog would be 2 dog minus 7. In general, we could say G of whatever is 2 times whatever minus 7. Whatever goes in there, goes in there. Okay. I want to go back for a minute and talk about the idea of domain and range. We could also call them input and output, x and y, independent variable, dependent variable. Now, what do I mean by that? Well, independent variable, the input is not controlled by the output, but the output is controlled by the input. Okay, so what goes in determines what comes out, not the other way around. Let's talk about what you wear and weather. Okay, let's say it's a cold day outside. You're going to put on a coat. You're not going to run around in your gym shorts. Well, some people do, but anyway, in general, you'd think if it's really, let's say it's snowing outside, you'd put on a coat, right? Or is it you put on a coat and walk outside, Mother Nature sees your coat and goes, oh, it's going to snow? No, your clothing does not control the weather. the weather controls what you wear. Okay, so the weather would be the independent variable, and what you wear is dependent upon the weather. So that's the output of the dependent variable. Another thing would be cause and effect. We could use the same example. The cause is the weather. The effect is what you wear, not the other way around. Okay. All right. Now, take a look at this example. It says, let f of x equal negative 2x plus 5. For what value of x does function f have the given value? All right, so for instance, we've got f of x equals negative 7. So let f of x equal negative 2x plus 5. For what value of x does function f have the given value? So now, instead of putting an input in to determine the output, they've told us that the output, don't forget f of x is another name for y, the output is negative 7. So what value of x do we put in to get a negative 7 out? What we're going to do is take negative 7 and put it in the place of f of x. So negative 7 equals negative 2x plus 5. Solving this for x, let's see here, we're going to subtract 5 from both sides, divide by negative 2, so we get x equals 6. So when 6 goes in, negative 7 comes out. So f of 6 would equal negative 7. But again, they've told us the outcome, we are to find the input. All right, let's take a look at another example of that. Let f of x equal 3/2 x minus 2. For what value of x does function f have the given value? And it says f of x equals 2/3. So what do we put in to get 2/3 out? So we already know what's going to come out, 2/3. So 2/3 is the result of what x value plugged in. So take this equation and solve it for x. Well, there's fractions. Let's clear the fractions by multiplying both sides by the LCD, which is 6. On the left, we get what, 12/3 or 4. On the right, 18/2 or 9x minus 12, distributing the 6. Add 12 to both sides, 16 equals 9x. Divide by 9, x equals 16/9. So that's the input that results in the output of 2/3. So the ordered pair, 16/9 comma 2/3, would be a point on the graph of this linear function. All righty. Well, that's all I've got for you today. I'll be back this afternoon at 1:15 with an office hour if you have any questions. Monday, we'll continue with section 8.2, part 2. Have a great weekend, and I'll see you all later.